Imagine a machine the width of a basketball court falling toward a planet with no solid surface. Below it, storms wider than continents twist through clouds thousands of kilometers deep. Around it, charged particles strike with enough energy to damage electronics hidden behind metal armor. The machine is moving at roughly 210,000 kilometers per hour. Then, near the most valuable part of the encounter, its scientific voice stops. That is the real tension behind Juno's closest passes over Jupiter. But the truth is more precise and more interesting than the headline. Juno did not simply vanish without a trace. It protected itself, and what happened during one especially difficult flyby reveals why exploring Jupiter is less like circling a planet and more like repeatedly diving through a natural particle accelerator. Stay with me, because we are going to separate the genuine record from the exaggeration, reconstruct the hours around the event, and see what this battered spacecraft has taught us about the largest planet in our solar system. If you enjoy calm, evidence-based journeys into deep space, subscribe and come with us. This matters for more than one spacecraft. Jupiter holds more mass than all the other planets combined, and it probably formed early enough to influence how much of the young solar system was assembled. Understanding its hidden interior is part of understanding why Earth ended up where it did. Every close pass is therefore a brief look into our own origin story. For years, scientists dreamed of seeing beneath Jupiter's famous bands instead of merely photographing their tops. Juno began that journey on August 5, 2011, when an Atlas V rocket carried it away from Florida. The direct distance to Jupiter can be hundreds of millions of kilometers, but Juno did not fly there in a straight line. Its 5-year route covered about 2.8 billion kilometers, or 1.7 billion miles. That is roughly 18 times the distance from Earth to the Sun, accumulated along a looping interplanetary path. The spacecraft first traveled beyond Mars, performed 2 deep space maneuvers in 2012, and then returned toward Earth in October 2013. It was not coming home. It was borrowing momentum. During the gravity assist, Earth's motion around the Sun increased Juno's speed by about 26,000 kilometers per hour. That boost was comparable to adding the speed of a fast-orbiting satellite without loading the spacecraft with the enormous amount of extra propellant a direct flight would have required. Juno then climbed outward again. Sunlight weakened as it traveled. At Jupiter, solar energy is only about 4% as intense as it is near Earth. Yet Juno relies on solar power rather than a nuclear generator. 3 arrays, each about 9 meters long, stretch from its central body. Fully deployed, the spacecraft spans more than 20 meters, similar to the width of a regulation basketball court. Near Jupiter, those huge panels originally produced only about 500 watts, roughly the demand of a few bright household lamps. That design forced discipline. Juno avoids long passages through Jupiter's shadow, keeps its power needs low, and spins for stability. During science operations, it rotates about twice each minute. The instruments are fixed to the body, so every spin sweeps their fields of view across Jupiter like the hands of a clock scanning a world. On July 4, 2016, after almost 5 years in flight, Juno reached the decisive moment. To be captured by Jupiter, it had to turn away from its usual sun-pointing orientation, increase its spin rate, and fire its main engine for about 35 minutes. Commands from Earth could not rescue a last-second mistake. Radio signals needed tens of minutes to cross the distance, so the spacecraft had to complete the sequence on its own. The burn worked. Juno entered a long, polar orbit that initially took about 53 days to complete. Instead of circling over Jupiter's equator like most earlier visitors, it approached over the north, crossed from pole to pole, and escaped over the south. At the far end of that stretched loop, it traveled millions of kilometers. From the cloud tops, then Jupiter pulled it back. The original plan called for a later engine burn to shorten the orbit to about 14 days. A concern involving engine valves made that maneuver too risky, so the team left Juno in the longer orbit. The close pass altitude and science quality remained useful, but the encounters came roughly every 7 weeks instead of every 2. What looked like a setback also reduced the frequency of radiation exposure and opened opportunities to study Jupiter's vast magnetic environment. The first fully instrumented science pass occurred on August 27, 2016. Juno swept to about 4,200 kilometers above the visible cloud tops. Pioneer 11, the previous record-holding flyby spacecraft, had passed about 42,500 kilometers above those clouds in 1974. In one generation, the gap shrank by a factor of 10. Later evolution of Juno's orbit carried it closer still, at times to around 3,500 kilometers above the clouds. If Jupiter were reduced to the size of a basketball, that clearance would be only about 6 millimeters. From that scale distance, Juno would appear to skim the varnish. There is an important qualification. Juno is accurately described as the closest orbiter to Jupiter, and NASA describes it as the first mission to make such low, repeated passes. But it was not literally the first human-made object to travel beneath that altitude. In December 1995, the Galileo mission released an atmospheric probe that entered Jupiter itself. That probe transmitted for 58 minutes while descending about 180 kilometers below its atmospheric entry level, until pressure and heat ended the signal. It was designed to die there. Juno's record is different. It is the closest surviving orbiter, returning again and again. Now here's something that surprises a lot of people when they first hear it. The most dangerous part of a Juno orbit is also incredibly short. For most of each loop, Juno is far from the planet. The crucial pole-to-pole science run lasts about 2 hours. During that window, the view changes from a distant striped globe to a curved wall of clouds and back again. At closest approach, gravity accelerates the spacecraft to around 210,000 kilometers per hour relative to Jupiter. That is about 5 times the speed of the Apollo spacecraft departing Earth for the Moon. At that velocity, Juno could cross the continental United States in little more than a minute if it were flying over Earth. Yet speed is not the main threat. Jupiter's magnetic field is at least an order of magnitude stronger than Earth's, and, in some regions, dozens of times stronger. The rapidly rotating field gathers electrons and ions, hurls them to high energies, and traps them in immense belts. A spacecraft passing through this environment is being struck by invisible particles that can flip bits in computer memory, confuse sensors, degrade camera electronics, and slowly damage solar cells. Juno carries armor for precisely this reason. At its center is a titanium vault about the size of an SUV's trunk. It weighs roughly 180 kilograms, comparable to 2 large adult humans, and contains the main computer, power electronics, and other sensitive assemblies. The walls are about 1 centimeter thick. The vault cannot stop every particle, but it slows the accumulation of radiation damage enough to give the mission a fighting chance. The trajectory is another kind of shield. Juno approaches from the north, threads a path between Jupiter and the worst concentrations of trapped radiation, and leaves over the south. Long elliptical orbits keep it away from the inner belts for most of the mission. The spacecraft does not survive by overpowering Jupiter. It survives by spending as little time as possible in the most dangerous neighborhood. Now stop and sit with that for a second. Engineers sent a solar-powered computer across billions of kilometers, gave it less electrical power than a small kitchen appliance, and asked it to repeat a 2-hour sprint through the harshest planetary radiation environment in the solar system on April 4, 2025, during Juno's 71st close approach. That environment appears to have pushed back. About an hour before perigove, the onboard system detected an anomaly and placed the spacecraft into safe mode. 45 minutes after perigove, it entered safe mode again. Safe mode is not the same as death. It is a survival reflex. Juno rebooted its computer, suspended non-essential activity, powered down its science instruments, and concentrated on power, thermal stability, and communication. It also pointed an antenna toward Earth. From the perspective of the science instruments, the encounter went quiet. From the perspective of mission control, however, the spacecraft had not simply become a lost, silent object. That distinction matters. The phrase "went silent" suggests that nobody knew whether Juno still existed. NASA's account says the opposite. During both events, the spacecraft behaved as designed and oriented itself for communication. High-rate data transmission was re-established, and engineers began examining the flight software and the engineering data. The valuable observations scheduled for much of that close pass were interrupted, but the protective system preserved the spacecraft. Early indications pointed toward the intense radiation belts encountered during the flyby, although that was described as an initial assessment rather than a final proof of one specific particle strike. By then, unexpected spacecraft-induced safe mode had occurred only 4 times since Juno reached Jupiter, once in 2016, once in 2022, and twice during this single 2025 encounter. In every case, the spacecraft recovered full capability. And this is where the story gets stranger. A system created to stop science may be the reason science could continue. When a computer on Earth encounters corrupted memory, a person can replace a component or restart a program. At Jupiter, there is no technician. A command cannot arrive instantly. Depending on the positions of Earth and Jupiter, radio waves take many tens of minutes to travel one way. A question sent from mission control and its answer can consume a large part of the 2-hour encounter, even if the spacecraft responds immediately. Autonomy is therefore not a luxury. Juno must recognize trouble, decide that the planned observations are less important than survival, reboot, find a safe orientation, maintain power from the distant sun, and establish a usable radio configuration without waiting for human permission. Safe mode looks like failure only if we judge the machine by the data it did not collect, judge it by the mission it protected, and it looks like engineering working exactly as intended. Close pass communication is complicated even when everything is healthy. Juno's microwave radiometer needs to face Jupiter to probe beneath the clouds. Its highest gain antenna cannot point everywhere at once. Much of the richest science is recorded on board for later transmission through NASA's Deep Space Network. What viewers experience as a live event is really a delayed reconstruction assembled from carrier signals, engineering telemetry, and stored data returned after the danger has passed. That also explains why dramatic images do not appear instantly. At closest approach, Juno is moving so quickly that every observation must be planned. Once the spacecraft is safely outbound, the information trickles across hundreds of millions of kilometers. The image that eventually reaches your screen is the final link in a chain. that begins with reflected sunlight at Jupiter, passes through a radiation-battered camera, becomes digital memory, and ends as a faint radio signal collected by a giant antenna on Earth. Here's the part almost nobody is talking about. The images are spectacular, but Juno's most important discoveries are often invisible. Its microwave radiometer listens to thermal radiation emerging from deep layers of the atmosphere. Its gravity investigation uses tiny changes in the spacecraft's radio signal to map variations in Jupiter's gravitational pull. A magnetometer measures the planet's irregular magnetic field. Particle and wave instruments sample the electric environment around the poles. Infrared and ultraviolet instruments study heat and auroras. Together, these tools turn the spacecraft itself into a moving probe of a world we cannot land on. Before Juno, Jupiter's colored belts and pale zones looked like weather painted on a surface. There is no solid surface beneath them. Juno's gravity measurements showed that the east-west jet streams extend roughly 3,000 kilometers below the visible clouds. On Earth, the deepest point in the ocean is about 11 kilometers. Down, Jupiter's banded winds penetrate hundreds of times farther than that, into pressures no aircraft could survive. The Great Red Spot is deep too, but not infinitely deep. Juno measurements indicate that the roots of the famous storm extend roughly 320 kilometers beneath the cloud tops. That is around 50 to 100 times the depth of Earth's oceans. The spot is enormous in width, yet its active structure is more like a vast, relatively thin lens than a cylinder reaching to the center of the planet. Juno also changed the picture of Jupiter's core. A simple textbook diagram might show a compact ball of rock and ice with clean layers of hydrogen above it. The measurements instead support a large, dilute, or fuzzy core, where heavier material may be mixed gradually into metallic hydrogen. It is less like a peach pit and more like dye spreading through a thick fluid. That structure carries clues about whether Jupiter formed a solid seed first, accumulated gas rapidly, or experienced a major collision early in its history. Here's the twist that changes everything that came before it. The dangerous close orbit is not just a way to obtain sharper pictures. Closeness is part of the measuring instrument. As Juno passes over regions with slightly different concentrations of mass, the planet tugs on the spacecraft by slightly different amounts. Those changes alter the frequency of its radio signal through the Doppler effect. The variations are tiny compared with its 21000 km/h flyby speed, yet they are enough to reveal the reach of the winds and the distribution of material inside Jupiter. Farther away, the signatures would blur together. The same principle helps measure the atmosphere. During a radio occultation, Juno's signal passes through Jupiter's ionosphere on its way to Earth. Charged particles and gases bend and delay the transmission. By measuring those changes, scientists infer temperature, pressure, and electron density at different levels. In 2026, an analysis of 13 Juno radio occultations found that Jupiter is slightly smaller and more flattened than earlier estimates suggested, about 8 kilometers less wide at the equator and 24 kilometers flatter at the poles. Against a planet roughly 140,000 kilometers wide, those corrections sound tiny. 8 kilometers is the scale of a town, not a world. But Jupiter's dimensions calibrate models of giant planets, including planets that pass in front of distant stars. Refining the shape of our local giant improves the ruler used to interpret alien giants across the galaxy. Water is another example. The atmospheric probe released by Galileo entered an unusually dry region and found far less water than expected. Juno's microwave measurements later estimated that, near Jupiter's equator, water accounts for about 0.25% of atmospheric molecules, close to 3 times the corresponding abundance. In the Sun, that does not prove the value is identical everywhere on Jupiter, but it showed that one descent through one dry patch could not represent the entire planet. Then there is the weather no one predicted. Juno found a central cyclone at the North Pole encircled by 8 more. Individual polar cyclones stretch thousands of kilometers across, comparable to the width of a continent, yet neighboring storms can remain arranged instead of immediately merging. At the South Pole, another geometric collection of cyclones has evolved while retaining an organized pattern. Lightning provided a second surprise. Researchers expected Jovian lightning to form mainly where water exists in liquid and solid phases, broadly analogous to thunderstorms on Earth. Juno detected shallower flashes at higher atmospheric levels. One leading model says ammonia lowers the melting point of water ice, creating an ammonia water liquid that allows electrical charging high in the clouds. The same model proposes slushy ammonia-rich hailstones, nicknamed mushballs, that fall deeper and transport ammonia and water downward. The mushballs are a scientific interpretation supported by several observations, not objects Juno directly caught and placed in a container. Jupiter's magnetic environment reaches far beyond weather. Its magnetosphere forms an immense obstacle to the solar wind, with a long tail extending outward through the solar system. In 2026, scientists reported that Juno had detected electrons accelerated to nearly the speed of light in the foreshock region ahead of Jupiter's magnetic boundary. The scaling of that acceleration matched processes suspected in much larger systems, including the environments associated with supernova-driven cosmic rays. A spacecraft built to examine one planet was helping test a mechanism that operates across the universe. Present-day stakes begin with the spacecraft itself. NASA currently lists Juno as an active mission, and observations and analysis continued beyond the endpoint once projected for September 2025. That does not make the spacecraft immortal. Radiation damage accumulates, hardware ages. Every pass spends a little more of a finite engineering margin, but each successful recovery converts risk into time and time into knowledge. JunoCam offers a vivid example. The color camera sits outside the titanium vault, directly exposed to the environment that the central electronics are armored against. It worked normally through the 34 orbits of the Prime mission, but by orbit 47 its images showed radiation damage. By orbit 56, most frames were corrupted with noise and streaks. With no replacement camera and no repair crew, engineers tried annealing, warming the hardware in hopes that heat would reduce microscopic defects in an electronic component. A mild heating cycle helped temporarily. Before a close I/O encounter in December 2023, the team pushed the heater harder. The pictures improved only days before the flyby, and JunoCam returned detailed views from about 1,500 kilometers above the volcanic moon. It was not a permanent cure. Image noise later returned, but the experiment turned a failing camera into a lesson for future radiation-tolerant spacecraft. It is the same philosophy as safe mode. Use the tools available, preserve what can be preserved, and never confuse recovery with magic. The mission has also become a pathfinder. Europa Clipper is traveling toward the Jovian system, and the European Space Agency's JUICE mission is on its way as well. They have different trajectories and goals, but Juno's experience with radiation, power, autonomous fault protection, and deep space communications informs the broader challenge of working near Jupiter. The icy moons are compelling because some contain subsurface oceans, and protecting spacecraft operations there is part of protecting future science. For us on Earth, Juno's measurements sharpen models of giant planets and magnetic particle acceleration. Those subjects may sound remote, but magnetic storms and high-energy particles can disrupt satellites, communications, and power systems here. Jupiter provides an extreme natural laboratory. If a physical process works across the scales of Earth's magnetic boundary, Jupiter's enormous bow shock, and the aftermath of exploding stars, then we may be looking at a general rule of cosmic particle acceleration. The close passes also teach a quieter lesson about evidence. A lost image is not evidence of a hidden discovery. A powered-down instrument is not the same as a destroyed spacecraft. A delayed transmission is not proof of a cover-up. Deep space exploration naturally produces gaps because spacecraft must balance pointing, power, memory, heat, and survival. The honest story can still be dramatic. In fact, the constraints make it more dramatic. Now we reach the most important reveal. Juno did fly closer to Jupiter's cloud tops than every earlier flyby spacecraft and closer than any previous orbiter. At times it came to about 3,500 kilometers, only a few percent of Jupiter's diameter above the visible clouds. It crossed that region at around 210,000 kilometers per hour while immersed in radiation. Capable of upsetting hardened electronics, during the 71st close approach, its instruments did go quiet when safe mode shut them down twice. But Juno itself did not simply go radio silent for mysterious hours. Its protective software rebooted the computer and pointed the antenna toward Earth. The high-rate link was restored. The spacecraft survived. The silence was not the unsolved mystery. The silence was the safety system doing its job. That is the real wow fact at Jupiter. Success is sometimes measured by the data a spacecraft chooses not to collect. Juno sacrificed part of one irreplaceable flyby so that the larger mission could continue. It gave up the moment to preserve the future. If this journey changed the way you see that headline, share it with someone who loves space and tell us in the comments which part surprised you most: the record-setting altitude, the radiation vault, the deep winds, or the spacecraft's autonomous recovery. Subscribe for more stories where the facts are powerful enough without being distorted. There is one more dimension of this story that deserves to be told. Juno's radio signal, the same thread that reassured engineers during danger, has become a scientific tool in its own right. It helped refine Jupiter's very shape. A transmission that seems like nothing more than a status line can be bent by an atmosphere, shifted by gravity, and transformed into measurements of a planet no human can touch. That may be Juno's most fitting legacy. It was sent to see through Jupiter's clouds, but seeing did not always require a camera. Sometimes it meant measuring a wobble in a radio tone. Sometimes it meant listening to particles. Sometimes it meant accepting a blank stretch in the data and understanding exactly why it was blank. Return to that first image. A fragile, spinning machine falling toward a wall of storm, its instruments suddenly still. It is not abandoned. It is thinking through a crisis at the speed of software, far beyond the reach of any repair crew. Then, across the darkness, the signal returns.